This course is Design of Column Reinforcement. We welcome you. We also welcome those who are attending by streaming. This session is being streamed live, so sometimes there'll be questions from them, and we welcome them. The PDH code for this session is 82142, as you can see on the screen. And this session is Design Column Reinforcement. And our speaker is Bo Dowswell. Bo has been in the steel industry since 1985. In the first 9 years as a detailer. He is a principal of ARC International, an engineering firm specializing in design and research for steel structures. He received a PhD in structural engineering for his research on gusset plates and is an adjunct professor at the University of Alabama in Birmingham. He is a professional engineer and has published several journal articles on steel connection design and beam stability. Bo is a member of the AISC Committee on Specifications, the AISC Committee on Manuals, and the AISC Committee on Industrial Buildings and Non-Building Structures. Please welcome Bo Dowswell.
Okay, thanks, Alan. Design of column reinforcement. And I kind of felt like when I made that title up that it was pretty self-explanatory, but this is what we're going to be talking about. You know, obviously there are a lot of different ways that you can reinforce a structure, and we're going to talk about this one specific way if you get down to where you want to reinforce your members with, for example, the reinforcing plates like I have shown in the picture on the left up there. Then this session is for you. We will be limited to axially loaded members. If you want further information on flexural members, you can take a look at this webinar that I'll show you the link to about halfway through the presentation. Okay, so what we're going to talk about, generally, everything has to do with flexural buckling. So we're pretty much going to be limited, at least in the discussion, to these wide flange shapes typically. So that's what I'll show in all of my pictures, I believe, are the wide flange column shapes. Now, most of the things that we'll talk about will also apply to other shapes too, but you can kind of figure out how to apply those to the other failure modes that you can get if you have, say, an angle column where you end up with maybe a torsional buckling or flexural torsional buckling or something like that. Okay, now with that, this is my favorite reinforcement type, the one on the left-hand side there. And the reason is because it's easy for me to design, and it's pretty easy to install. You only have 2 plates, and typically that edge between the flange tip and the plate, you can make that big enough, maybe 1 inch or so, where they can get some room in there. I think if you look in the AISC manual, it might say somewhere around a 1/2 inch or so for certain size welds on the land, but you want to give them room to move that plate around a little bit in the field too. So that's my favorite type. The one on the right-hand side, if I need a little more strength or buckling, stiffness for buckling about the y-axis especially, without increasing the plate thickness, I might go to the one on the right, but that one's a tiny bit harder to install sometimes because a lot of times, obviously, you're going to have members framing into the web of that member You'll have beams and struts framing in, and potentially vertical bracing, gusset plates. And in this case, the welder for this one, he's just out here. He has a lot of room to weld, and this one, he might be slowed down a little by the obstructions in the web. So that's why that's kind of my second choice. Now we're kind of getting into the second tier, where if you need to, you go to one of these. The one on the far left is a singly symmetric reinforcement, and of course, being that that's less efficient, you would probably only want to use that when you have access only to one flange. And I'll show you another disadvantage later on. It has to do with weld shrinkage, the distortion due to weld shrinkage. The one in the middle, obviously that's going to be good for torsion because it makes a closed shape out of the wide flange, but also it increases the weak axis properties for weak axis buckling a significant amount too. The problem is that you always have something framing into the web there, and at least in the structures that I typically work on, industrial structures, you're also going to have vertical bracing gusset plates to contend with there too. So you might have to cut those significantly short. I'm not saying that you wouldn't have to do that for the flange plates either, but just kind of keep that in mind, especially if you're going for torsional stiffness there. You're going to have a very stiff torsional section, and then when you cut it back, you're going to go to a very non-stiff torsional section. The one on the far right is my least favorite, but sometimes I have to use it. What happens is that sometimes your load is so high that you can't set the reinforcement back. And I'll show you in the next section. We'll talk about the setbacks, where you set the reinforcement back from the work point. But if you absolutely must have continuous reinforcement through, say, a beam framing into the web and or the flange here, that's probably the only way to do it, is something similar to this, if you have framing on all four sides to get that continuous reinforcement. And then with this slide, I kind of just wanted to throw a lot of things up there just to let you know, we're not limited to just the ones that I've shown you. You can do whatever you want. It's up to you to use your judgment to come up with a way to reinforce this column and the best way that gives you the right strength and stiffness, and also satisfies the owner's requirements. For example, I mean, obviously this one's going to be pretty good for weak axis buckling, but watch out for weld clearance problems here. You can flip it around this way, but you're going to maybe lose space out on the floor. You're gonna cut a few inches off of the usable space. One thing you can do is just kind of get a wider channel here to make sure that they can get access in there. This one, an architect may want you to do this so that he doesn't lose floor. If you want to keep everything within the perimeter of the column, you can do something like that. But again, watch out if you get too close for the distance between these angles. You can, again, end up with weld clearance problems where you can't get in there and make the weld properly. This one is kind of goofy, but we'll come back to that later. I put that up just to kind of show you the types of things that you can do. All right, so now let's talk about what we're going to talk about. We're going to spend just 2 slides talking about the AISC specification, flexural buckling provisions in Chapter E. The reason we're spending such little time on that is because I think everybody should be familiar with that already. And then we'll move on to really what the presentation is about. One of the topics is going to be partial length reinforcement, as I alluded to earlier, where you have to set it back to avoid a beam or a strut or a gusset plate. Then we'll go into some fairly interesting information on preload that allows you to design your columns a little easier and get more strength out of them. And then really my favorite part of the presentation is this notional load analysis, and that's because it's kind of a new thing. It's not so much new for researchers, but it's kind of new to be used in practice other than for the direct analysis method. And then we'll use that notional load analysis to talk about weld design, because that's always a question that we get. I'm a consultant with the AISC Solution Center, and we get that question a good bit. How do I design welds for columns? If it's an axially loaded member, it's kind of trying to figure out what the required strength of that weld is kind of a problem. Let's go ahead and get a review on this AISC specification. And these equations, like I said, should be familiar to everybody. Section E3 is the flexural buckling section, and it's the one that we typically go to for wide flange columns. And of course, I know that everybody's used to just putting in the software and trusting the software to do these equations for you. But we need to kind of take a look at it just so we'll know what the variables are once we get further into the presentation. So we've got a critical stress times the gross area, and this top equation up here, or the middle one, is going to be your inelastic buckling stress. And if you're in the elastic range, you'll use this equation, and you'll notice that both of these have the variable F sub E in it. And F sub E is just your, I call it the elastic or the Euler buckling stress, and it's given by this equation. And this should be familiar to everybody too, because really this is the 2016 version. You're probably used to seeing a KL here instead of L sub C, but L sub C is KL. So it's the effective length of the column. And I don't know, but I'm assuming that that was changed because a lot of the columns are being designed using the notional load method, or the direct analysis method would probably be a better way to do it, better way to say it, where you're using an effective length factor of 1. So that's probably why that change was made. But in our case, we're gonna do it both ways. We're gonna use the K of something other than 1, and then later on in the presentation, I'll show you how we can use K equals 1. Now let's move on to the partial length reinforcement like I talked about earlier. And this is what you often, unless you want to dismantle the whole building, which would, of course, cause you to probably put a new column in rather than reinforce the existing column anyway. So you're going to have to pull back. If you have flange reinforcement and beams coming in or struts, you're going to have to pull that reinforcement back. Your work point is, you're probably going to consider that your work point for the column buckling. And so that's going to be pulled back maybe, somewhere close to a foot or something. And then there are situations where I've gone in and said, well, let's pull that back 3 or 4 feet just for economics, get less weld, less plate, and the column strength doesn't require it, then that can save money, and it can save column distortion, weld shrinkage distortion too. Now, typically, if I pull it within 2 or 3 inches, usually I'll give them about 3 inches there just to give them plenty of room to move it around. And if I end up with something that looks like that, typically I just neglect it. I neglect that setback dimension. And the reason is because it's kind of braced all in this section, and you're really only unbraced from here to here. So what difference is that going to make? And also, it's at the end of a column. The main part that's going to contribute to the strength of that column is at the center of the column, at the mid-height, I should say. Okay, but when you get something like this, which is usually the case for me because I have vertical brace gusset plates I have to contend with on most every project, the right-hand side there, you will end up pulling your reinforcement back maybe 50% of the distance between work points from here to here. And typically, if I can get by with it, usually I'll just put the same plate on both sides. Even if this one can run all the way up, usually I just give them the same plate. So what we do, it's just like everything else. We have to take something that we really do not know that much about and try and model it as something that we know something about. And it's not necessarily that we all know something about stepped columns, but we're going to model these reinforced columns with a setback as a stepped column. All right, so the reason that this is handy is because we have tables for this. We can go directly in and pull the effective length out of the tables. And the tables, the ones that I use, I'm sure there are more out there, were published in 1969 in the AISC Engineering Journal. And it's this is kind of what the tables look like. I've rearranged everything and changed the variables to make it more for reinforced cross sections. And you can see all the variables at the top of the table, and you're going to pull out a K factor from this part of the table over here. But you can see that it's the K factor, the effective length factor, is dependent on the moment of inertia ratio, I sub R over I sub O in this column. And it's also dependent on L sub R over L for the next column. Another thing you'll notice is that there are two effective length factors in there, K sub S1 and K sub S2. So let's see what all of this is about before we can go into the tables. Okay, the I sub R over I sub O ratio, the moment of inertia ratio. All you have to do is take the moment of inertia of this reinforced section, I sub R, and the reinforced section, the non-reinforced section moment of inertia is I sub O, and you can get your ratio from that. So it's pretty simple to calculate that moment of inertia ratio. And the length ratio is really even easier because it's just L sub R over L, where L sub R is the length of the reinforcement and L is the total length of the column. Okay, the K sub S1 value, you'll pull that one out if you have reinforcement pulled back at one end of the column. The bottom end on this picture goes all the way to the work point of the column. The top end is pulled back. K sub S2 obviously is going to be the case where you pull the reinforcement back at both ends. One thing I will mention at this point, that we'll talk more about later, is that the table only handles equal distances for this D sub R dimension, the setback dimension. Now we have all the information we need to go into the table. We have the moment of inertia ratio, and in this case, it's 2.5. And let's say that we cover about 50% of our column with the reinforcement. So we're going to have an L sub R over L ratio of 0.5. And if we have reinforcement pulled back equal distances at each end, we'll pull out this value 1.139 for K sub S2. So with that number, all you have to do is take the reinforced section properties, go into the AISC specification that we just showed you, the E3 section, and use this effective length factor to calculate L sub C, and you're done. Okay, now that we can move on to the preload. First off, I really need to, this can get a little bit confusing, so I really need to talk about the two different cases for preload. Preload is the load that's on the column at the time that you reinforce it. So you've got a load that's on there when you reinforce that column, and the reason for reinforcing is that you're trying to add load. So after the reinforcement's added, you're going to add load to it then. So I guess you've got preload and postload on the column. But there are two cases that I'm going to show you. One is that you can kind of ignore the effects of that preload, and that's when you have stabilizing reinforcement. When you have stabilizing reinforcement, you can take the preload and the postload, add those two together, get your total load, go into the AISC specification, and calculate the strength of the column, and you're done. All right, so if you do not have stabilizing reinforcement, you have to figure out another way to do it. Probably the old allowable stress method is the only way that I know that's available right now. So what I typically do is try to get the stabilizing reinforcement, and the way to do that is to make sure that your reinforced radius of gyration, R sub R, is greater than or equal to 85% of R sub O, which is the non-reinforced radius of gyration. It's the original cross-section radius of gyration. So just in practical terms, the one on the left, that's almost always going to be stabilizing reinforcement. We can go back to the definition of the radius of gyration. Remember, it's the square root of the moment of inertia divided by the area of the cross-section. So if you add a lot of area without adding a significant amount of moment of inertia, then you're going to have a non-stabilizing reinforcement. Now, I will mention this. This is everything that we're going to talk about for this slide is going to be for weak axis buckling. Actually, this works for both strong and weak axis to be stabilizing almost always. But I will say this. Let's say that you have a 14-inch wide flange and a 3-inch wide plate. It's not going to provide much increase in, it's going to provide a decrease in your radius of gyration significantly due to the addition of the area without a significant increase in the moment of inertia. So you can run the numbers and make sure that you get to that 0.85 number or better. And this one is going to be non-stabilizing. Remember, we said we would come back to this one, the one on the right-hand side. The reason, and this is for weak axis only, the reason is because you're adding almost no moment of inertia to this thing about the weak axis, and you're adding area. Okay, so let's kind of take a step back now that we've kind of gone over what the stabilizing reinforcement is and kind of a little bit about how to use it. The figure on the left, let's say we load that. Let's say it's a really short column. We load it to 90% of its yield strength, the gross area times the yield stress. Or if you're in Europe, you call it the squash load. So 90% of the squash load, and that's without reinforcement. Let's say the non-shaded portion of that cross-section gets loaded to 90% of its squash load, and you leave the load on there, and then you add the plates. You weld the plates on, and then you add another 500 kips or so. So obviously, this is going to turn to mush. This is going to be inelastic. This whole non-shaded portion is going to be inelastic. And inelastic material has an extremely low modulus of, well, it's not even called the modulus of elasticity, an extremely low stiffness. I guess I'll call it the inelastic modulus. I'm sure that the theoretical guys will correct me on that. But the shaded portions of this are going to remain elastic. So the plates, the reinforcing plates, are going to be elastic. And if you think about it, and even if you do go into some of the old theoretical textbooks that talk about, I believe it's the tangent modulus theory. Is that right? The tangent modulus theory, where you go in and basically you say you have an extremely low, or in some cases the authors have said zero stiffness for your yielded portion, and use the 29,000 for E for your elastic portions of the cross section. So what we want to do is get the elastic portions of our cross section as far away from the neutral axis as we can. And that's what the stabilizing reinforcement concept is all about, is getting the elastic portions of our cross section to be the most efficient to prevent buckling of this column. Okay, and I just thought I would throw this in just for fun on the right-hand side here. That's a BRB, kind of a concept of a BRB, which is a buckling restraint brace. And I'm by far not a seismic expert, but I do know how these behave. What they're trying to do is get, so you've got a core, you put that in tension, it's going to yield. And you want to be able to put that in compression and have it yield at roughly the same strengths, the same strength as it yields in tension. So to do that, you have to put basically continuous bracing along the length of that core. And you can see that in the far right figure, kind of where the casing is restraining that member all along the length. So the casing, at least theoretically, has no stress in it. So that's kind of the same concept. You're using kind of a casing to restrain this yielded portion of the column here. Now, what I will say, as far as design goes, if you have stabilizing reinforcement, once again, you just go into the AISC specification and design using the preload plus the post load as your total load, and that's all you have to do. Otherwise, you have to account, if you have non-stabilizing reinforcement, you have to account for that load that's on that column at the time of reinforcement. And the way we had always done it ever since I had been in the business is use the allowable stress design, where you take the stress that's on the column and then you reinforce it, and then you proportion that stress based on the reinforced cross section. And there's an example of how to do this in the this 2013 webinar. The part 1 shows how to do this design of reinforcement for steel members. There's 2 parts to it. The second part talks about local buckling and a few other things like that, welding. But it's at the AISC website at that link. And you can get the notes, the PDF notes, and also view the webinar for free, I believe. And I think if you want to come back and get the credits for your PE license, I think you have to pay for that. Okay, so we know how to do these. If we want to break it up into this preload concept and the stabilizing reinforcement and all this stuff, so we know what to do with it now. But let's take a look at the test results for this. Now, in addition to these test results, the University of Alberta put out a report where they did over 300 finite element models, and this method works. The finite element models showed that this method works that I've just showed you. I think they had up to about 60% of the axial strength of the column as the preload in some cases. So yeah, that was a good. Actually, what we did is we plotted all those results and came up with the 0.85. Okay, but it's even more fun to look at the experimental results. This one in 1963 we'll talk about first, and then we'll briefly hit the 1990. It's all based on this, what they call the Type C reinforcement, which of course is my favorite. So I was glad to see that it was somebody else's favorite too. Okay, the top row, these are all the specimens. The top specimen up here, the one that's shaded, is not reinforced. The one below that, T17, is reinforced, but it has no preload. And the one below that, T13, and these are all the same, basically the same columns. They're not the identical columns, but they're the same cross-section and the same reinforcement in the case of the T17 and the T13. Okay, so T13, you load it up to 91 kips, and then you add the reinforcement, and then you load it up further until it fills at 528 kips. Okay, so we've got the preload here. Slenderness ratios, you can see, are all about what we'd expect to see in a normal structure. The test load is here. The calculated load is here. That's using the actual yield, not the nominal yield stress, but the measured yield stress from their tests. And the ratio is here, the test to calculated ratio. So that final column is going to tell the story, and anything bigger than 1, as all the values are, is going to be conservative. But it's kind of interesting to look at the specimen T9. It's 3% conservative compared to the AISC specification curve. And this none of these values account for preload. It's all based on this total load on the column, P sub T or P sub C, and it's all based on the AISC specification, section E3. Okay, so we're 3% conservative, and that's not a surprise. I was surprised that it was a little bit lower than I thought it would be compared to this column, but there are a few things to take into account. Of course, you've got some potential errors that you can get in the testing, and you can also get, we don't really know what the out of straightness values are for these columns, so that can greatly affect the buckling strength also. So let's look at, these next two are really interesting. The next one is 1.09, so you get 6% or so more strength by adding reinforcement. Remember, this one is the same column basically, but it's reinforced. So you get 6% more out of it. And the reason for that, at least theoretically, like I said, there are other things that can explain the differences, but theoretically, what happens is if you have a wide flange shape, you're going to have compression residual stresses at the flange tips. And compression at the flange tips, remember the flange tip is the area that we're most interested in to contribute to the efficiency of this column to prevent it from buckling, okay, to provide resistance to buckling. So the flange tips are farthest in both the weak axis and the strong axis from the neutral axis. Okay, so we want those to be elastic as long as we can, but a compression residual stress plus a compression applied load is going to cause it to yield earlier than if you had no residual stresses. All right, so that's your normal condition, and that's the AISC column curve. Is based on a lot of different shapes, but also it includes a lot of the wide flange shapes with compression residual stresses. Okay, so you add a weld here near the tip of that flange, and a weld causes really, really high tension residual stresses. It doesn't matter what was there before. It doesn't matter much. It kind of totally blows that out of the water and does its own thing. So you end up with compression originally, and that changes to very high tension residual stresses. And so that's the theoretical explanation for the 6% increase between those two specimens, because it's going to yield at a higher load if you have the tension residual stresses, and that when it yields, it loses the stiffness, the resistance to buckling. Okay, so that was pretty interesting, but this one is even more interesting, and I do not have a theoretical explanation for this one. T13, we put a preload. Now, I said we put a preload on there, but that was done in 1963, and I was not alive then, so I couldn't have put a preload on this myself. But the authors put a preload of 91 kips on this, and they ended up with a bigger test load than the specimen T17. Okay, I'm not sure why that is, but you can see the ratio over here is 1.11, so it goes up 2%. So my wild guess is that it just had a little bit less out of straightness to the column. Okay, really quickly on the rest of these specimens, the preload was somewhere close to 100 kips, you can see there, and all of these were conservative by at least 3%, and there's one that was conservative by 27%. So at least the test results showed that this stabilizing reinforcement concept, which, by the way, all of these specimens met that requirement, that it works. So that's going to, if you do it that way, it's going to really make your design easier. For one thing, you can just put the properties in your finite element model and forget about it. You know, you don't have to go back and do all these stress calculations on the cross section based on the preload. And sometimes we even ended up back in the day when we were doing the other method, the allowable stress method. You know, you might end up with two finite element models. You might end up with one that's going to give you the load before it's reinforced at the time of reinforcement, so that you can use that stress, and then another finite element model with the final properties on there. So you kind of get the idea. It just really saves a lot of engineering time if you do it that way with the stabilizing reinforcement. And plus, it gives you more accurate loads and much higher loads in a lot of cases. All right, my favorite part of this, it's actually the strangest part of the presentation, is the notional load analysis. But let's go over some advantages of using notional loads, and then I'll show you what we're talking about. I think everybody knows what the notional load analysis is from the direct analysis method. It's been in the spec long enough where what you do is with the direct analysis method. And the reason I call this notional load analysis instead of direct analysis method is because there are some differences that we'll talk about. For one, we're talking about pin columns right now. We'll kind of keep the discussion to that. But for the direct analysis method and AIC specification, you're going to try to you're going to apply a horizontal point load at the floor levels typically. Wherever your load is, wherever your vertical load is, you're going to apply a horizontal notional load. And what that notional load does is that it simulates the moment that's in the column or in the frame members due to the sway imperfection of that frame, due to the out of plumbness of the frame. So the notional load is based on the Code of Standard Practice maximum imperfection in a frame. Okay, so that kind of the ones that weren't familiar with the direct analysis method, that kind of gives you an introduction. We're going to use a slightly different method here, and I'll show you why. But the advantages, the first advantage is that it allows you to evaluate any cross-section along the length of the column. When we did and I'd never thought about it before because I was using that effective length method in practice for, I don't know, a couple of decades or so. And I never really thought about what it was doing, but really all you're checking when you do that is that mid-height cross-section. If you have a symmetrical column, all you're checking is that mid-height because that's the buckling location. This method, you can also check, which I've found controls sometimes, these other critical sections at the end of the reinforcement. All right, I alluded to this one earlier. You can use the notional load method to evaluate columns with different setbacks. Now, in the past, we were limited to the effective length method, which had equal setbacks at each end of the column, either 0 or equal at each end of the column. And of course, you just had to use your judgment and usually just went with the biggest setback is what, of course, most structural engineers would do. But in this case, you can do anything you want. You can do, in fact, you can put the reinforcement at the bottom and the top and have none in the middle if that's what you want to do. Okay, now this is an important one. It gives you the ability to directly evaluate the reinforcement welds. When you weld that plate to the flange of that member, you need to know what load is in that plate or what load you're going to design for the shear flow. We'll talk about that in the next section. And I briefly said something about this earlier too. The weld shrinkage distortion can cause the column potentially to have a larger out of straightness than what is allowed in the AIC Code of Standard Practice. And typically, if you're welding on both sides, I typically just rely on the welders to, you can stagger the welds, and I'm not sure how they do it. It's kind of an art. The guys in the shop or the field would know a lot more about it. And there's information in Blodgett's book and several other references on this too, if you want to look into it. But if you have reinforcement on both sides of this flange, they can kind of stagger their welding. They can weld, and I don't know, I'm probably getting this wrong. They can weld here and then go up and weld over here some and then come back and weld here to limit the distortion to that member caused by the weld shrinkage. And with this single-sided reinforcement, you're not going to be able to do that quite as much. There's only a limited amount of things you can do. So if you do end up with a larger out of straightness for this column than is allowed in the Code of Standard Practice, you can't just use the AIC specification equations. You have to include some extra moment in there, and this method allows you to do that. Okay, I talked about notional loads earlier for the direct analysis method, but we talked about point loads, concentrated loads at the level of the floor to simulate the out of straightness of the frame. Now, in this case, if we have a pin column, we can do the same thing, but in our case, we're trying to simulate the moments in the column due to the out of straightness of the column. And to best do that, we would apply a uniform load through the entire height of the column, like I've got shown W sub n in the figure. And to get the value of that, let's say you're within that you meet the requirements of the Code of Standard Practice, which are L over 1,000 for the out of straightness. Delta sub D is what I've called it. Then you can use this equation to calculate your notional load. P sub R, which is the required axial load on the column, divided by 125 times the length of the column. If your out of straightness exceeds the value in the Code of Standard Practice, you can use this slightly more complicated equation that has P sub R in there also. It's got 8 times P sub R times delta sub D, which is the out of straightness after welding, divided by L squared this time instead of just L. So both of those values are going to give you fairly small loads. So what I typically do is I'll apply those loads about both the X and the Y axis. And of course, you're going to end up with a moment diagram that looks something like this about both axes. Now here's the part where you kind of have to make sure that you're awake because there are a lot of details that you need to look at in this. And one is that you need to use the reduced value for EI, and it's called EI star, and this is used in the direct analysis method in the AIC specification, section C 2.3. It's given as 80% times tau sub B times the actual E times I. All right, let's take a look at what tau B is. This is straight out of the specification. Now, a lot of times you're going to be at that top one where tau sub B is 1. And the reason is because you've got your axial load on the column, P sub R. This is 1 for LRFD, the alpha. And your P sub NS is what I called earlier the squash load. It's the yield stress times the gross area. And that's assuming that you have non-slender cross-section, which we would typically have in the types of structures I do anyway. If you do not have non-slender, if you have slender cross sections, then you have to account for local buckling in that P sub NS, but we won't go there. So a lot of times, being that that's the squash load, you're going to be in this range and end up with tau B equals 1. Otherwise, you'll use this equation, which we've already discussed the variables in that equation. It's fairly easy to apply. Okay, we're going to use that reduced value for EI, the EI star, over to the right-hand equation over here. We're going to use that to calculate the Euler load. And the other thing to note when calculating this P sub E1 is that L sub C, as I mentioned earlier, is going to be calculated not with a K of 1.139 from the table, but it's going to be calculated with K equals 1 because we're accounting for all of the factors that went into the effective length factor with this notional load method. So L sub C is the actual length of the column. Use K equals 1, just like you would with the direct analysis method. Okay, so then this should be familiar to everybody, the moment multiplier equation. We're going to use that P sub E1 we just calculated, divide that into the actual column load, P sub R, I guess in the official terminology is the required load on the column. And we end up with a number bigger than 1 there for B sub 1, and we multiply our moment, M sub NT, by that to get our required second order moment. I will say that M sub NT, if all you have on your column is the axial load, the M sub NT is going to be based on those notional loads, that uniform notional load over the height of the column. So you would add that if you do have additional moments on your column, you would add those two together. Okay, this is the hand calculation method, and this is the method that I've used before. But you know, being that I'm not that computer savvy, so I kind of do the hand calculation method unless something really comes along to make me want to change it. And as it turns out, after I kind of started looking at this, using this the second order finite element analysis, it's really going to give you a little bit more accurate answers because you don't have to do an estimate on EI on the properties for that. But it's very easy to do. And what I typically do for a finite element analysis, if I'm doing this, I do not typically add this to my giant finite element model with all the everything in it. Usually I'll just make a separate finite element model with one column in it, and I'll break that column. The first thing I'll do is I'll put a node, the nodes at the ends, and then I'll break it up at the reinforcement ends, wherever the reinforcement ends at the theoretical cutoff point that we'll talk about in a minute. I'll put nodes there, and then I'll just break the rest of it into either 5 or 10 different segments and do a second order analysis on it. And then, but this is so much easier because the software I use will do all of these iterative calculations for you. It'll calculate the second order moment, and then it will design everything for you. So you basically, it's one of those things where if you get everything in there right, you just press the button and you're done. All right, let's move on to what we do with all these loads. Obviously, we have biaxial bending and compression. So what we'll have to do is combine it. And the way we do that, and the reason that it's okay to just put it in and press the button in the finite element software, is that we're using the AISC specification equations that are used in the software. So we go into spec section H1.1 and pull out these equations that should be familiar to everybody, where you combine biaxial bending and compression. The one difference, now for column shapes, mostly you're going to be dealing with, we know what the required moments are. The X and the Y, they're based on any moment that's on there plus the notional load moment. We know what the required axial load is, and usually these are going to be the plastic moments about the X and the Y axis for column shapes anyway. Typically you're going to be using the plastic modulus to calculate those loads. In other words, no lateral torsional buckling, no local buckling. This piece of C, okay, don't go in and treat this like a normal combination. You do not have to account for slenderness effects on the column for that. The piece of C is going to be replaced with this piece of NS that we talked about earlier, the squash load in the column, just the yield stress times the gross area. And of course, any local buckling effects if you have that. So that's one of the other tricks, the important tricks that you have to remember to do this. And before we move on to the weld design, I'll say that if you go through everything that I've done, just for a normal column, not a stepped column or a reinforced column or anything, just for a normal column, if you want to check to make sure this method is accurate, you can put it in and go through all of the steps that I've just shown, and you should end up with something extremely close to the AISC equations that we went over at the very beginning of this presentation for flexural buckling. And the reason is because this was the equations, especially that reduction equation, was meant to simulate that. So it's basically a way to simulate that column curve. And that's why I was saying earlier that it's really interesting. You know, I tried to avoid this notional load method for years, hoping that I would have to retire before I had to learn it. But it ended up, once I figured out that it was all based on things that made sense. You know, once you dig into it, you see why everything is the way that it is. You know, there's, for example, you know, you apply the load, that accounts for the out of plumbness of the column. So you can look and see where everything comes from, and it really makes sense. And it really kind of turned a light on when I did exactly what I told you to do, is just do for a normal W14 at 90 column and do everything I just said, and you'll end up with very similar results to what you would get with the AIC specification equations. All right, Carlo and I in the AIC Solution Center get a question on weld design for axially loaded members, I don't know, once a month or so. And of course, there's always the question, you've got an axial load in the member and no moment. So how do you design the welds? You know, of course, if you have a beam, you're going to use the VQ over I, the shear flow. So what do you do if you only have axial loads? And of course, if you weld a plate to a wide flange member and there's no weld there, you need it to act together. So obviously there has to be some load in that weld that you need to account for, but there's just not really a way looking at the picture up here to figure it out. So what we're going to do is we're going to go through and we're going to calculate a shear flow over this length, just like you would a beam. Shear flow over this length, L sub RT, the length in the middle, and then what I call an anchor force, the required force over this length, D sub RT, at the ends of the reinforcement. Now, we'll go ahead and mention this theoretical cutoff point. Typically, your theoretical cutoff point, if you're not familiar with that term, it discusses it some in the, I think it's in the commentary to the AIC specification. But what you would do in your model, whether you do it by hand or in a finite element model, that's the theoretical cutoff point is where you would end your reinforcement in that model. Okay, but you need to extend it beyond that to develop the load that's in the stiffener or in the plate beyond the theoretical cutoff point over length D sub RT. All right, so the reason I put the weld design section after the notional loads section is because we have to use notional loads to do this. So we're going to apply our notional loads. For this one, there's not going to be any shear flow due to this notional load, so we can just apply it in this direction if this is all you're looking for. And then we can either do a finite element model and do the second order effects, or we can go in and do the moment multiplier equations and go into the AIC manual and pull the equation straight out of the tables. And in this case, here's our notional load up here. We're going to have a theoretical cutoff point somewhere over here. So our shear is going to be somewhere in that range, and our moment's going to be down here. But typically, these loads are so small that I just calculate just based on the maximum shear in the moment on a real project. You know, if I were going to do it for a presentation, I would probably go ahead and do the full calculation, but it's just the loads just aren't big enough to worry about unless you have a giant high-rise building. Okay, so we've got the shear, we got the moment. We're going to call it V sub R, and I think I call it M sub R C on the next one. So V sub R, we take our shear just like we would a beam. Now that we've got that notional load on there, it is a beam. So we treat it just like a beam. VQ over I, go to strengths of materials class. And you remember that equation from strengths of materials, but I took off the T. You remember it was VQ over IT gave you a shear stress in a beam. You take off the T and it gives you a shear flow or a kips per inch instead of a KSI. And so we're going to say V sub R times Q over I sub R. And I sub R, of course, is going to be your reinforced cross-section moment of inertia. And Q, going straight back to our strengths of materials course, is going to be the area of that reinforcement times the distance between the centroids of the reinforcement and the centroid of the built-up member. And for the anchor force at the end of the reinforcement, it's very similar. And I don't remember covering this in sophomore level strengths of materials class, but it's very similar to get the force at the theoretical cutoff point. You just replace the V sub R with this M sub RC. So MQ over I gives you the anchor force. The Q and the I sub R are the same, and the M sub RC is the moment at the theoretical cutoff point. But that's only due to the moment. To get the axial load in the reinforcement at the theoretical cutoff point, we can kind of just use, I wouldn't even really call it a mechanics problem. I would just call it kind of a, one of those things where you just use common sense. And all I've done is I've taken the total reinforced area of the column, the required axial load, and divide the area into the load to get the stress. And that's P sub R over A sub R. And then to get the load in the reinforcement, just multiply by the, I've called it A sub RI. So all we're trying to do is distribute that stress into the plate to figure out how much load is in that plate based on that stress diagram. Obviously, you're going to want to add the two, add the anchor force due to the moment and the axial load. And we'll take that and develop it over this distance d sub rt at each end. And being that that's the load on one plate, but we have 2 welds per plate. So you're going to take that, divide it by 2, and then divide by d sub rt. And that's going to give you the kips per inch on your weld at the end. Now, one thing you can do is you can weld across the top and the bottom if you want to develop this load too. But typically I don't do that, just to stay away from overhead welds down here at the bottom. All right, it looks like we've saved the fun stuff for last. The quiz, and this is one of those things where it's kind of a all or nothing thing, just a 1-question quiz. And the question is, which statement best describes notional load analysis of reinforced columns? All right, and the I'll show you the multiple choice answers on the next page, but I always used to hate that when it used to say which one best describes, because it was always a trick question. You had to read all of them. Okay, A. Notional load analysis is required when using the 2016 AISC specification. B, it has several advantages over the effective length method. C, a second order finite element analysis is always required. Or D, all of the above. Got anybody that's brave enough to step out there? All right, let's see. Oh, it looks like we're going to take it step by step. All of the above is not right. We got to have some suspense, right? Okay. A, obviously it's not required in the spec. The specification says nothing about using notional load analysis for reinforced columns. And C is not true either, because you can use a second order analysis or the hand calculation method to get the second order effects. So B, it has several advantages over the effective length method. All right, it looks like we're over to our conclusions, and we'll just say that columns with partial length reinforcement can be designed with either the effective length method or the notional load method. The effective preload can be neglected when the geometry meets the stabilizing reinforcement requirement. And like we just learned from our final exam, notional load analysis has several advantages over the effective length method. And finally, welds should be designed for both the shear flow and the anchor force. And Alan, that concludes the discussion. Do we have time for questions?
Yeah, we have a few minutes. I think there's questions here.
Yeah, a lot of questions online.
Okay.
Go back to the preload table.
Okay. Now, is this the table with the experimental results?
Yes, from the 1963.
Okay.
The question was, is PC nominal strength or E times PN?
Okay, what was the question?
Is PC nominal strength or E times PN?
Okay, that was a good question. I forgot to mention that. Okay, the question is does PC include a safety factor or a fee factor in there, or is it just the nominal strength from the AISC specification? And the answer is that it's the nominal strength. It has no safety factor and no fee factor included in the P sub C value right here. Okay, any more online? Okay, are there any questions that we can take out here?
You had a stabilizing force ratio, R sub R over R sub O, I think it's greater than or equal to, again, what was that ratio to determine whether it was a stabilizing?
Okay, it has to be, okay, R sub R, let me go back to that. R sub R has to be greater than or equal to 85% of R sub O, where R sub R is the reinforced cross-section properties, the radius of gyration, and R sub O is the original cross-section properties. Yeah, here it is. Okay, the question was about the exact nature of that equation. Okay, anything else? Yeah, in the back.
It's about the same ratio. So are you saying if I meet this requirement, then I can ignore all initial load stresses in my section and analyze it as an entire section afterwards? That makes sense.
Okay, yeah, the question is if we meet this requirement, does that mean that we can just treat this as a normal column with the total load on it, going into the AIFC specification section E3, calculate the flexural buckling, and basically we're neglecting the effect of the preload. Obviously, we take the preload, add it to the post load, get the total load, go into spec section E3. So the question was, is that what this is for? And the answer is yes. Yeah, if you meet this requirement, you treat this, you basically take the preload and ignore any stresses that are on that cross section at the time of reinforcement and take the preload, add it to the post load for your total load.
We got another question online. What about using bolts instead of welds? What changes in the analysis?
Okay, bolts. Okay, the question was, if you use bolts instead of welds in the analysis, does anything change? And I'm not sure about that, because the one thing I would say is that you really need to use slip critical bolts to prevent slip between the reinforcement and the column, because what that's going to do, if you do not use slip critical bolts, essentially what you're going to do is, once you get that moment due to the notional load in there, it's going to try and it's going to make the initial imperfection really big before that engages, because the bolts have if both bolt holes are oversized by 1/16, then you can get a pretty big movement in there, and that's going to translate into a large rotation before those bolts engage. So I would say definitely use friction bolts, and in that case, if you did use friction bolts, I would think that everything would be the same as what I've discussed. But I would probably have to spend a little more time to think about it, think about all the repercussions of doing that. So I would just say use your judgment, and if you want to contact me, they've got my email address, so I think they can contact me if they want to discuss this further, or they can just I'm a consultant with the Solution Center. They can just send it into the Solution Center, and we'll talk about it there. Okay, it looks like we're about 4 minutes over, so do you want to cut it off right there? And I'll stay up here if anybody has any further questions.